Let's learn how to associate a graded algebra to a filtered algebra. Let's assume we have a field K and we have an algebra A over K. Now assume the algebra A is filtered, which means that we have some subspaces labeled by integers. They form a chain, and such that the chain ends covering the whole of the algebra. The crucial condition is that the subspace Fm multiplied with elements in the subspace Fn is again a subset of the space Fm plus n. This is a filtration of the algebra A, which is now a filtered algebra. Corresponding to the filtered algebra A, we have an associated graded algebra. The graded algebra is defined as follows. Graded associated algebra to A is equal to the direct sum of graded subspaces. And the graded subspaces are defined as follows. G0 is just F0, but for n bigger than 0, we have that Gn is Fn divided by Fn minus 1. The definition of the product on the graded algebra is that if we have an element of Gn and we multiply it with an element of Gm, we get an element xy inside Gm plus n. In other words, now we preserve the grade. And therefore, G of A is a graded algebra. Let's study two examples. Example 1. Suppose that we have already a graded algebra, which is a direct sum of pieces given grade. And of course, we get a filtration by setting Fn to be the sum from I 0 to n of AI. Easy to check that this is a filtration. So from a graded algebra, we automatically can get a filtered algebra. This is fairly trivial. What we see is that if we have an element of Fn, we should only concentrate on the part which is top degree. And when we multiply two such elements in Fn times an element in Fm, then we concentrate on the top degree multiplication. This is how we obtain the graded algebra. Example 2 is slightly more interesting. Suppose we have a group algebra, so linear combinations of elements in a group, as well as a length function on the group, which associates a length 0 to the identity element, a length to a group element which is equal to the length of its inverse, as well as satisfying the property that the length of G times H is smaller or equal than the length of G plus the length of H. To extend this function to the group algebra by linearity and taking the top length, we can then define the filtration in the group algebra such that we put in Fi all linear combinations of group elements such that the length of the group elements appearing in the combination is smaller or equal than I. Because of the last property of the length function, this defines a filtration of the group algebra. Then we can descend to the associated graded algebra, which turns out often to be interesting depending on the length function that you can choose on the group. So this is a non-trivial and interesting example, and there are many more.